Hello, I'm going to go through quickly an overview of the Lorenz gauge potentials. So this is material from chapter 10 of Griffiths, and it sort of will summarize the results of the beginning of chapter 10 on what do potentials look like in electrodynamics, and then go through how do you actually calculate them in Lorenz gauge, and what does that mean. So just a quick recap. What sort of potentials do we have? We had in earlier chapters, we had the scalar potential V and the vector potential B. And starting with the vector potential, one of Maxwell's equations is that the divergence of B is zero. That's the statement that there are no magnetic monopoles. And because B is divergenceless, we can write it as a curl. Writing B as the curl of A guarantees that its divergence is zero, but it's also always possible to write it as the curl of A. And in fact, it's possible to write it as many different curls, or as the curl of many different vector potentials. And then in electrostatics, we had a nice scalar potential V that was very helpful to us. But in electrodynamics, we have Faraday's law that tells us the curl of E is not zero. And if the curl of E is not zero, then E cannot be the gradient of a scalar, because the gradient of a scalar is always curl free. So what do? We can actually take our result from the vector potential and plug it into Faraday's law and find out that the curl of the combination of E plus dA dt, E plus A's time derivative, has zero curl according to Faraday's law. Therefore, that combination can be written as the gradient of a scalar, and I can adjust the formula for E to show that E is minus grad V minus dA dt. And so the new term there in the definition of the scalar potential is that I have to include the vector potential also. So the vector potential just got a big upgrade. It used to be only useful for the magnetic field and not super useful at that. Now it's essential. We need it to compute both the magnetic field and the electric field in electrodynamics. So how are we going to do it? Well, let's write down Gauss's law in terms of potentials. It's got this new term here that comes from that dA dt in the definition of the electric field. So this is Poisson's equation, but kind of modified. What's the Ampere-Maxwell law look like? It's kind of a mess. I've got a whole bunch of terms, and it depends both on the vector potential and the scalar potential. So all these equations are all mixed up. They're not separated for V and vector A, and they've got these nasty terms in them. So what are we going to do? The answer is we're going to simplify, and we get to simplify by picking a gauge. Remember that a gauge is just the fact that we can choose different potentials to represent the same fields. So back in chapter 5, we chose lots of different vector potentials to give the same magnetic field, and we proved that you could always pick one where the divergence of A was zero. Divergence of A shows up twice in these equations. It'd be great to get rid of it, so let's try it out. That gauge choice is called Coulomb gauge. So let's try it. Coulomb gauge. That's the statement that divergence of A is zero. That simplifies Gauss's law into exactly Poisson's equation. So that's what we solved in chapter 3. This is actually a different equation because both sides are now functions of time, but there are no time derivatives anywhere. So the solution is exactly the same. V is an integral over the charge distribution, 1 over r superimposed, weighted by how much charge there is at different places. We've done this integral lots of times, and it's actually exactly the same answer from electrostatics. There's no change. But that's not enough to calculate E. We also need to know A. How do I calculate the vector potential in Coulomb gauge? Oh, you don't. It's awful. That equation depends both on V and on A. So you've got to calculate V first, plug it back in, and then it's not a simple solution. It's not analogous anymore like it was in magnetostatics. So that's not so great. Instead, we're going to pick a new gauge. We're going to be inspired to try and simplify the Ampere-Maxwell equation so that we can actually get the vector potential out. And the best thing we can do is look at that parenthetical term, the gradient of this thing equals zero, or the gradient of this thing is the nasty bit, the Ampere-Maxwell law. So maybe we can use our gauge freedom to set the divergence of A plus epsilon naught mu naught dv dt equal to 0. And it's not necessarily obvious that that's always possible, but it is. And you can go through the textbook or prove it yourself that it's always possible to make this choice. What happens, we greatly simplify both. Poisson's equation gets a little more complicated. Now it has time derivatives, but Ampere-Maxwell law is exactly as complicated or as simple, depending on how you look at it. And V and A now have a parallel structure. The scalar potential is determined just by the charge density. The vector potential is determined just by the current density. And the only complication we had is that now there's some time derivatives hanging around. So what are we going to do? The first thing that you should notice is the left-hand side of this looks like the wave equation. But the right-hand side is not equal to 0, it's equal to something. And in differential equations, that means that it is an inhomogeneous equation. So these equations are called the inhomogeneous wave equation. They're Maxwell's equations, but we've reduced them to a form that has a mathematically known structure called the inhomogeneous wave equation. So how do we solve it? How to solve the inhomogeneous wave equation, we're going to guess the answer. And so we're going to be inspired to guess based on the fact that electromagnetic waves travel at the speed of light. And so if I move a charge around, the change in the field should propagate at the speed of light. And so what that means is that the vector and scalar potentials at this point, r and t, depend on the charge and current density over there at r prime and t sub r in the past. So I want to know the current values of V and A depend on the past values of rho and j. It takes time for that information to get over from there to there. And how much does it depend on? That value TR is the current time minus the light travel time. So the distance between those 2 points, script r, divided by the speed of light. So T sub r is historically called the retarded time because it's a time in the past that was delayed in catching up to the present. And historically, its use in these equations that we're going to write down led to them being called the retarded potentials. I like to call them the Lorenz gauge potentials because they are in Lorenz gauge. And that's an important thing to remember. So what are we going to do? We're going to guess the simplest thing. We're going to write down Coulomb's law for the potential, but we're going to change T to T sub r. That's all. So the charges still produce 1 over r potentials at their location, but we record the potential at a point based on the value of the charge distribution at a time in the past. The time in the past, T sub r, depends on how far away that point is. So it looks nice and simple. It's not so simple to calculate. The formula for the vector potential is exactly the same thing, but it depends on j instead. That's because they are the same equation. They should have the same solution. How do we know it's the right thing? We check it and it works. We take the time derivatives of this thing. We take the spatial derivatives of this thing. It's a mess. Griffiths does it. You can show that it satisfies the inhomogeneous wave equation. So great, we found the solution. And in fact, we found the solution to Maxwell's equations. If you have any time-dependent charge and current distributions, you can plug those in to these formulas, the Lorenz gauge potentials, and find the present values of the scalar and vector potentials, take their derivatives to find the electric and magnetic fields. You're done. You solve the problem. Carrying that out is a process, but it's not possible. We have the solution in general for Maxwell's equations. A couple notes about that solution. T sub r, the retarded time, is a function of both position variables. It's a function of both the field point and the source point. And don't forget it. It's subtle. It's lurking there. When you take the derivative of one of these formulas, you're going to have to plug through and use the chain rule and take extra derivatives of T sub r. A related fact is that we guessed this answer for the vector and scalar potentials. Why didn't we try it for by replacing T with T sub r in the electric and magnetic field formulas? And the answer is it won't work. We basically got lucky. That's the power of these potentials, is that they have a very nice simple solution, whereas the fields don't. So here's an example. If I took Coulomb's law, it would look something like this. So I would be integrating over the charge density at some time times script r hat over script r squared. That's our old friend Coulomb's law. And instead of evaluating the charge distribution now, I would evaluate it in the past at T sub r. And that's what we would guess, and it would not satisfy Maxwell's equations. In fact, when you take the derivatives of v and a that you need to, you end up with two more terms, one that depends on the time derivative of rho and the gradient of the retarded time, and one that depends on the time derivative of j. Those extra terms are real, they're physical, they have measurable consequences. The second one there is related to radiation. There's a lot of stuff going on that we wouldn't have guessed, whereas our simple solution for the scalar and vector potentials just gave us the right answer. And it gives us these extra terms when we take its derivative. So we got kind of lucky that we were able to guess the solution so easily. And it's a lot of work to show that it's the right one, and it's a lot of work to use it in practice, but now you know what it is. And this is a general way that you can solve Maxwell's equations if you know the charge and current. There's an example problem in the next set of lecture notes. You're going to find the electric and magnetic fields of a wire carrying a current that suddenly turns on. That's an electrodynamic situation because the current's a function of time. It was zero and now it's not. And you're going to find both electric and magnetic fields, both of which depend on time. And you're going to have to compute those potentials first using the Lorenz gauge potentials. So let me know if you have questions, and good luck.